Right now, one of the most important measurements in all of science is refusing to behave. The James Webb Space Telescope was expected to settle an argument that has followed cosmologists for more than a decade. Instead, its sharper infrared vision removed one of the easiest explanations and left the deeper problem standing. Nobel Prize-winning physicist Adam Riess and his team used Webb to recheck the stars that anchor our measurement of cosmic expansion. The result was not a new picture of a hidden planet or a mysterious object drifting through space. It was stranger than that. Webb found that the nearby universe still appears to be expanding faster than the standard model predicts from the universe's earliest light. Riess's documented warning was not literally, "This isn't our universe." His actual statement was more careful and more unsettling. Once major measurement errors are removed, there remains a real possibility that we have misunderstood the universe. Today we are going to break down exactly what Webb measured, why two versions of cosmic history refuse to match, what scientists think may be missing, and why this does not mean the Big Bang has been disproved. No guessing, no dramatizing, just the facts, the measurements, and the real stakes. Drop a comment right now. What was the first space discovery that made you stop and rethink your place in the universe? Tell us what it was and when you first heard about it. If you want the full picture, whenever a major discovery changes what we think we know, subscribe. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so more people see the science behind the headline. Now, let us get into it. The story begins with a number called the Hubble constant. Despite the name, it does not describe a fixed speed that every galaxy shares. It describes how the recession speed of a galaxy increases with distance as space itself expands. In everyday language, more distant galaxies are generally carried away from us faster than nearby galaxies. The conventional unit is kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. If the Hubble constant were 73 kilometers per second per megaparsec, a galaxy 1 megaparsec away would participate in the cosmic expansion at roughly 73 kilometers per second, while a galaxy 100 megaparsecs away would recede at roughly 7,300 kilometers per second before local motions are carefully accounted for. This number influences estimates of the universe's age, size, composition, and future. It also tests whether the mathematical model used to connect the hot early universe to the present day is complete. For decades, astronomers expected better instruments to make all reliable methods converge. That is normally how precision science works. Noise shrinks. Calibration improves. Independent teams approach the same answer. But in this case, the error bars narrowed while the central values stayed apart. The disagreement became known as the Hubble tension. One root, built from the early universe, points to a value near 67 or 68. Another root, built from stars and supernovae in the later universe, repeatedly lands closer to 73. A difference of roughly 5 or 6 units may sound small. In precision cosmology, it is enormous. To understand why Webb matters, we have to climb what astronomers call the cosmic distance ladder. No tape measure can stretch across millions of light years, so researchers build distance estimates in overlapping steps. The first rung uses objects whose distances can be measured geometrically. One crucial anchor is the galaxy NGC 4258. It contains a disk of water vapor orbiting a supermassive black hole. Radio observations of these natural masers trace their motion with enough precision to give a geometric distance. Another anchor is the Large Magellanic Cloud, where eclipsing binary stars help establish distance. Parallax measurements from the Milky Way provide another foundation. The next rung uses Cepheid variable stars. Cepheids brighten and dim with a regular period. More than a century ago, Henrietta Swan Leavitt discovered that the pulsation period reveals a Cepheid's true luminosity. If astronomers know how bright a star really is and measure how faint it looks, they can infer its distance. Cepheids are therefore not just beautiful stars. They are calibrated mile markers. The next rung reaches Type Ia supernovae, stellar explosions bright enough to be seen across vast stretches of the universe. Cepheids in a supernova's host galaxy calibrate the explosion's true brightness. Astronomers then compare many calibrated supernovae with their redshifts to determine the present expansion rate. Every rung must be tested because a small bias near the bottom can propagate upward. Hubble transformed this work, but Hubble also faced a serious limitation. At the distances of supernova host galaxies, Cepheids can appear crowded against a background of unresolved stars. Imagine trying to measure one candle in a stadium while thousands of smaller lights blur around it. Extra background light can make the candle seem brighter, and a brighter-looking standard candle can appear closer than it really is. Critics of the high local expansion rate asked whether crowding in Hubble images had biased the Cepheid measurements. This was not a fringe objection. It was a practical, testable concern. James Webb was designed with a much larger mirror and powerful infrared instruments. At the wavelengths used for these measurements, Webb can separate stars more cleanly than Hubble. It was the ideal independent referee. In Webb's images, Cepheids that looked embedded in mottled patches through Hubble became more distinct. The scatter in their period-luminosity relationship dropped dramatically. If crowding had created the high value of the Hubble constant, Webb should have shifted the distances enough to ease the tension. That did not happen. The measurements from the two telescopes agreed. The suspected error was reduced, yet the disagreement with the early universe prediction remained. That changed the argument. Webb did not prove exotic physics. It did something more disciplined. It removed a major hiding place for ordinary error. The 2023 Webb analysis compared hundreds of Cepheids in NGC 4258 and NGC 5584, a galaxy that hosted a well-observed Type Ia supernova. The telescope's sharper vision reduced background contamination and tightened the Cepheid relationships. The distance measurements agreed closely with Hubble. Then the team expanded the test. More than 1,000 Cepheids were observed across the geometric anchor and 5 supernova host galaxies. The formal difference between the Hubble and Webb distances was effectively zero within the uncertainty. The researchers reported that unrecognized crowding in Hubble's infrared Cepheid measurements could not explain the tension. In the language of statistics, they rejected that specific crowding hypothesis at more than 8 sigma in their 2024 analysis. 8 sigma does not mean every possible systematic error has vanished. It means this particular proposed mechanism, a distance-growing crowding bias in the tested measurements, failed a very strong check. Webb was not simply repeating Hubble. It was looking with a different mirror, different detectors, different resolution, and different infrared behavior. Agreement across those systems gave astronomers greater confidence that the late universe distance ladder was measuring a real feature rather than a single instrument's flaw. But here's the part that makes the title feel so unsettling. The better the telescopes agreed with each other, the more sharply they disagreed with the prediction derived from the universe's infancy. That early universe prediction comes largely from the cosmic microwave background, the oldest light we can observe. It was released when the universe was about 380,000 years old, after the primordial plasma cooled enough for electrons and nuclei to combine into atoms and light to travel freely. Satellites such as Planck mapped tiny temperature variations in this background across the entire sky. Those variations encode the density of matter, the amount of ordinary matter, the geometry of space, and the physics of sound waves moving through the young plasma. Scientists then fit the data with the standard cosmological model, usually called lambda cold dark matter, or Lambda-CDM. Lambda represents dark energy in its simplest form, a cosmological constant. Cold dark matter provides the invisible gravitational framework on which galaxies grow. With a small set of parameters, the model explains an extraordinary range of observations. When Planck data are interpreted within Lambda-CDM, the inferred Hubble constant is about 67.4 kilometers per second per megaparsec. The SH0ES distance ladder program, led by Riess, has measured a value near 73. Recent integrated local distance analyses reported a nearby universe value around 73.5. The exact values depend on the samples and methods, but the pattern is clear. The late universe often looks faster than the early universe model expects. To put that difference in context, imagine 2 highly accurate clocks describing the same journey. One clock is set using a photograph taken near the beginning. From that starting image and a trusted model of the route, it predicts when the traveler should arrive. The second clock measures the traveler directly near the destination. If the traveler keeps arriving earlier than predicted, there are 3 broad possibilities. The starting photograph was interpreted incorrectly. The destination measurement is biased. Or something happened during the journey that the route model does not include. Webb attacked the second possibility by checking the late universe measurements. Planck and other cosmic microwave background experiments have faced their own extensive checks. Neither side can simply be declared wrong because the numbers are inconvenient. That is why scientists use the word tension rather than contradiction or collapse. A tension is a statistically meaningful mismatch between data sets or inferences that may still be resolved by improved calibration, sample selection, or theory. The title's phrase, "This isn't our universe," should not be read as a claim that we live in a simulation, a parallel cosmos, or the wrong timeline. The scientific issue is narrower and more profound. The equations that describe how our universe evolved may be missing a component, a transition, or an interaction. Adam Riess became central to this story long before Webb launched. In the late 1990s, 2 teams studying distant Type Ia supernovae discovered that cosmic expansion is accelerating. Riess was part of the High Supernova Search Team. Saul Perlmutter led the Supernova Cosmology Project, and Brian Schmidt led the other team. Riess, Perlmutter, and Schmidt shared the 2011 Nobel Prize in Physics for the discovery of accelerated expansion. The result introduced dark energy as the name for whatever is driving that acceleration. Dark energy is not directly seen like a glowing object. Its existence is inferred from how the expansion history behaves. More than 2 decades later, Riess's team is again using supernovae, this time to test the expansion rate today. The verified NASA wording behind the dramatic title is crucial. Riess said that, with key measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe. That is not the same as saying all cosmology is wrong. Scientists often use strong language when a robust discrepancy survives repeated tests. It means the current model may be an approximation, just as Newtonian gravity remains extremely useful, even though general relativity describes gravity more completely in extreme conditions. The local measurement itself is not one single observation. It is a network of calibrations. Cepheids connect geometric anchors to supernova host galaxies. Type Ia supernovae connect those hosts to the smooth Hubble flow farther away, where local gravitational motions are a smaller fraction of the total recession speed. Researchers correct for dust, metallicity, detector response, crowding, pulsation phase, supernova properties, and the motion of galaxies relative to the expanding background. Every correction has uncertainty. That is why independent methods matter. The tip of the red giant branch uses a sharp change in the brightness distribution of old red stars. J-region asymptotic giant branch stars offer another potential standard candle. Mira variables, surface brightness fluctuations, gravitational wave standard sirens, and time delays in gravitational lenses provide additional routes. Some analyses using Webb data have found values closer to 70, potentially reducing the tension. A 2025 Chicago Carnegie analysis combining 3 stellar methods reported a value around 69.96, with uncertainties large enough to overlap the standard model. Its authors argued that the model may be holding up. Other teams have criticized aspects of sample selection and have found that combining larger or different samples returns values above 72. This disagreement is not a scandal. It is the active scientific process, and it is why the strongest statement is not that Webb solved the Hubble tension, but that Webb made the debate more precise. One reason teams can reach different values is that the available Webb sample is still smaller than the decades-long Hubble sample. A handful of supernova host galaxies may not perfectly represent the full population. The calibrating supernovae themselves have intrinsic scatter. Different methods can share some anchors and some systematic uncertainties even when they appear independent. A result near 70 can sit statistically between Planck and SH0ES, easing the conflict without proving either endpoint wrong. Meanwhile, a larger Cepheid-based dataset can produce a value near 73 with a smaller formal uncertainty. The correct comparison must include covariance, calibration choices, anchor uncertainties, and whether the same supernovae appear in multiple method samples. Simple headline arithmetic can exaggerate certainty. The most responsible conclusion is that Webb has strengthened confidence in Hubble's Cepheid photometry and exposed a real methodological divide over how to combine the expanding set of distance indicators. In April 2026, an international collaboration described a local distance network that integrates multiple markers according to their robustness and reported about 73.5 kilometers per second per megaparsec. That result again supported a faster nearby universe. But even a consensus local value would not identify the missing physics by itself. It would only sharpen the question. Another independent Webb clue came from a gravitationally lensed supernova. In a massive galaxy cluster, gravity bends light and can create multiple images of the same distant explosion. Because each light path has a different length and passes through a different gravitational potential, the images arrive at different times. If astronomers model the mass of the lensing cluster and measure the time delays, they can infer the Hubble constant without using the traditional Cepheid ladder in the same way. Webb discovered a Type Ia supernova that appeared in 3 locations through gravitational lensing. A preliminary analysis reported a value around 75.4, with broad uncertainty. The error range was too large to settle the issue, but the central value was consistent with other local measurements. This method is powerful because it carries a different collection of systematics. It is also difficult. The distribution of visible and dark matter in the cluster must be modeled accurately. Small changes in the lens model affect the time delay distance. More lensed supernovae will be needed. Still, the result shows how Webb is expanding the debate beyond one ladder and one set of stars. The telescope is not finding a single object labeled new physics. It is building a web of cross-checks. Webb has also found that the early universe itself was busier than many astronomers expected. It has confirmed luminous galaxies at redshifts above 13 and 14, meaning their light began its journey only a few 100 million years after the Big Bang. Some galaxies appear brighter, more massive, or more chemically developed than early models predicted. Deep fields are filled with compact objects called little red dots, many of which may contain rapidly feeding black holes. Other strange galaxies show gas emissions so intense that the gas can outshine the stars. These discoveries are sometimes bundled together online as proof that the Big Bang is broken. That is premature. Early galaxy models contain uncertain astrophysics: how efficiently gas cools, how quickly stars form, how massive stars behave, how dust changes observed colors, and how black holes contribute light. Several initially alarming galaxy candidates moved to lower redshift or lower mass after spectroscopy and better modeling. A 2024 spectroscopic study of massive dusty galaxies found no direct conflict with Lambda-CDM in its sample, although a few galaxies required remarkably efficient conversion of ordinary matter into stars. The surprise may lie in galaxy formation rather than fundamental cosmology. Webb's early galaxy discoveries and the Hubble tension are related through the history of the universe, but they are not the same problem. The phrase "found something strange" therefore describes a pattern, not a single photograph. Webb is revealing a universe that formed structure quickly, grew black holes efficiently, and continues to challenge the predicted expansion rate. None of these findings alone overturns Lambda-CDM. Together, they identify places where the model's simple ingredients may need richer physics. Lambda-CDM remains successful because it explains the cosmic microwave background, large-scale galaxy distribution, gravitational lensing, nucleosynthesis, and much of structure formation with remarkable economy. A model can be extraordinarily successful and still incomplete. The orbit of Mercury did not make Newton useless. It revealed a small discrepancy that general relativity eventually explained. The ultraviolet catastrophe did not make all of classical physics worthless. It pointed toward quantum mechanics. Scientists are cautious with these historical comparisons because cosmology may still resolve its tensions through measurement details. But the logic is the same. Persistent residuals are where new understanding often begins. What kind of new physics could change the expansion history? One candidate is early dark energy. In the Standard Model, dark energy becomes important relatively late, after matter has thinned as the universe expands. Early dark energy models add a temporary energy component before or around recombination. This can alter the sound horizon, the physical scale imprinted in the cosmic microwave background. If the sound horizon is smaller than standard Lambda-CDM predicts, the same observed angular pattern can support a larger Hubble constant. The challenge is that any new component must improve the Hubble tension without spoiling the excellent fit to the microwave background, galaxy clustering, nucleosynthesis, and other data. Many simple early dark energy models help one dataset while creating tension elsewhere. New observations from the Dark Energy Spectroscopic Instrument, the Atacama Cosmology Telescope, and future microwave background experiments continually tighten the allowed space. Early dark energy remains an active idea, not an established discovery. Another possibility is that dark matter has properties beyond the cold, collisionless particles assumed in the Standard Model. It might interact weakly with dark energy, decay over cosmic time, or include a small warm component. Additional light particles, sometimes described through an effective number of relativistic species, could change the expansion rate before recombination. Neutrino physics may play a role, although current constraints are strong. Primordial magnetic fields have also been explored because they could influence the ionization history and the inferred sound horizon. Modified gravity offers another route. General relativity has survived every major test, but cosmological scales are difficult to reproduce in a laboratory. A subtle change in how gravity behaves over billions of light years might alter growth and expansion. Each proposal must pass a brutal set of tests. It must reproduce the observed microwave sky, the abundance of light elements, galaxy clustering, gravitational lensing, supernova distances, and the ages of the oldest stars. The missing ingredient cannot be inserted only where convenient. It must tell one coherent story. There is also a more conservative possibility. The disagreement is a combination of small systematics distributed across several measurements. No single error needs to be large. A slight calibration offset in one anchor, a population effect in supernovae, an unmodeled metallicity dependence, selection bias in host galaxies, and assumptions in the early universe model could add in the same direction. Webb's tests make one major crowding explanation less plausible, but cosmology at 1% precision is unforgiving. A 1% shift can matter. That is why the community has not declared a revolution. Researchers are repeating measurements with different filters, different stellar populations, more supernova hosts, and new geometric anchors. They are reanalyzing the same public Webb data with independent pipelines. They are testing whether the apparent tension changes when samples are selected by distance, galaxy type, or data quality. The honest scientific position sits between two bad extremes. It is wrong to say there is no problem because Lambda-CDM has been successful. It is also wrong to say Webb has destroyed modern cosmology. The evidence supports a genuine unresolved discrepancy whose interpretation is still contested. The numbers themselves help show why this matters. A Hubble constant of 67.4 and a value of 73.5 differ by roughly 9%. Because the Hubble time is approximately the inverse of the expansion rate, a higher value corresponds, all else being equal, to a shorter characteristic expansion timescale. In a full cosmological model, age also depends on matter and dark energy, so it is not as simple as dividing one number. Still, the tension affects the reconstructed timeline. It changes the inferred physical size of the sound horizon and the calibration of distances across the universe. It influences how we compare supernova surveys, baryon acoustic oscillations, galaxy clusters, and gravitational wave events. Cosmology is a connected system. Pull one parameter and many other constraints move. That is why a disagreement of a few kilometers per second per megaparsec can occupy entire conferences. The issue is not that galaxies are suddenly racing away in a way humans can feel. The issue is that our most successful equation for connecting cosmic infancy to cosmic adulthood may not land on the measured present. The human side of the story is easy to miss because the measurements are so abstract. A Cepheid in a distant spiral galaxy may appear as a few infrared pixels. A type Ia supernova may be one point of light among billions, yet teams spend years calibrating those points. They schedule observations, monitor variable stars across multiple epochs, subtract backgrounds, compare detectors, model dust, and blind parts of analyses to reduce unconscious bias. Competing groups challenge one another's assumptions. Papers are revised, error bars are enlarged or reduced. An apparent discrepancy may disappear after a correction, or it may survive and become more important. This is not uncertainty as weakness. It is uncertainty measured, exposed, and attacked. Webb was built partly to see the first galaxies and characterize exoplanets, but its resolution also makes it a precision instrument for testing older telescopes. The fact that Webb agrees with Hubble on Cepheid distances is a triumph for both observatories. The uncomfortable part is what that agreement implies for the model connecting those distances to the early universe. What should we watch next? First, the Webb Cepheid sample will continue to grow. More supernova host galaxies reduce sample variance and allow direct comparisons across crowded and relatively clean environments. Second, Tip of the Red Giant Branch and JAG-B programs will refine their 0 points and test whether their current differences are statistical or physical. Third, additional lensed supernovae and quasars will improve time delay cosmography. Fourth, standard sirens from merging neutron stars and black holes may provide distance measurements independent of the traditional ladder, especially when an electromagnetic counterpart identifies the host galaxy. Fifth, the Nancy Grace Roman Space Telescope is designed to survey enormous areas with Hubble-like sharpness and is expected to transform supernova and gravitational lensing statistics. NASA has indicated that Roman will extend the investigation with a vast new dataset. Sixth, new cosmic microwave background measurements and galaxy surveys will test the early universe side with higher precision. A solution must emerge from convergence, not from one dramatic image. Keep an eye on how headlines describe future results. A paper that reports a value near 70 may be called the end of the Hubble tension. Another paper using a different sample may report 73 and be called proof of new physics. Both can be statistically consistent with their own uncertainties. Ask 4 questions. What method was used? How many calibrators were included? Which anchors and supernovae were shared with earlier work? Was the result peer-reviewed, preliminary, or a press summary? Also ask whether the authors measured the Hubble constant directly or inferred it within a model. The Planck value is not a direct speedometer reading of today's universe. It is an inference from early universe data under Lambda-CDM. The local ladder is not model-free either, but its assumptions are different and more astrophysical. The tension exists because these distinct routes should agree if the measurements and the connecting model are all correct. Now we can resolve the title's central question. James Webb did not discover evidence that this is literally not our universe. It did not photograph another cosmos, prove a multiverse, or show that reality has changed. The verified warning from Nobel laureate Adam Riess is that we may have misunderstood part of our own universe. Webb's sharper images supported Hubble's Cepheid distances and weakened the argument that stellar crowding created the high local expansion rate. Subsequent Webb work added more cross-checks, while other teams using different stellar methods found values that may ease the disagreement. The field remains divided because the data are becoming more precise, faster than the interpretation is becoming simple. That is the strange discovery. Not one impossible object, but 2 credible cosmic histories that still do not meet. The largest fear attached to this story is that all of cosmology has collapsed. The evidence does not support that. The Big Bang model, cosmic microwave background, expanding universe, dark matter framework, and general relativity continue to explain an enormous range of observations. The realistic possibility is narrower. Lambda-CDM may be missing physics, or precision measurements may still contain subtle biases. Either outcome would be scientifically valuable. If a hidden systematic is found, astronomers will learn how to measure the universe more accurately. If the tension survives every independent test, it may point toward a new field, particle, interaction, or phase in cosmic history. For now, the correct response is not panic. It is attention. The universe has not changed. Our ability to interrogate it has. And that is why Webb's result matters. A telescope launched to look deeper into space has forced scientists to look harder at the assumptions beneath their own equations. The mystery is not solved, but it has become cleaner. One major source of error has been tested. Multiple methods are now competing at unprecedented precision. New observatories are preparing to join the investigation. The next decisive clue may come from a variable star, a lensed explosion, a gravitational wave, or a tiny pattern in the oldest light. Until then, the strongest conclusion is also the most honest. Something in the connection between the early universe and the present may still be missing. If this investigation changed how you think about cosmic certainty, share your first unforgettable space discovery in the comments. And if you found the full picture useful, help us reach 5,000 likes so more people see the evidence rather than only the headline. No filler, no guessing, just the facts and the full picture. Let us go. See you in the next one.